In the deepest laboratories beneath the Earth, where silence reigns and cosmic rays cannot penetrate, scientists pursue the most elusive quarry in existence. A particle so fundamental that without it, reality itself would collapse into meaningless chaos. This is not merely another subatomic discovery waiting to be cataloged. This is the search for the final piece of creation's puzzle, the ultimate binding force that prevents the universe from dissolving into primordial nothingness. Every atom in your body, every star burning in distant galaxies, every grain of sand and drop of water exists because of forces we can measure but cannot fully comprehend. We know of four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Yet something deeper must exist. Something that explains why these forces themselves cohere, why the fabric of space-time maintains its integrity, why quantum fields don't simply collapse in a void. The search has consumed decades of human genius and billions of dollars in scientific infrastructure. It has driven physicists to build machines that recreate the conditions of the universe's first microseconds, to peer into dimensions beyond human perception, to question whether reality itself might be nothing more than an elaborate illusion. And now, in laboratories scattered across continents, in data streams flowing from particle accelerators and deep space observatories, patterns are emerging that suggest we stand at the threshold of the most profound discovery in human history. The final particle may not be what we expected. It may not even be a particle at all. But finding it, or failing to find it, will determine whether our universe is eternal or merely a fleeting accident in an infinite cosmic dance of creation and destruction. The God particle's shadow the story begins not with a dramatic discovery, but with a profound realization, one that would shake the foundations of modern physics and launch humanity's most ambitious quest for understanding. In 1964, when Peter Higgs first conceived of the field that bears his name, he unknowingly opened a door to mysteries far deeper than the origin of mass itself. The Higgs field permeates every corner of existence, giving substance to particles that would otherwise remain massless ghosts dancing through empty space. Yet, even as the Higgs boson was triumphantly discovered at CERN in 2012, physicists found themselves staring into an abyss of incompleteness. The God particle had been found, but it was merely the shadow of something far more fundamental, something that holds the very architecture of reality together. The trail began in the 1970s when Gerard T. Hooft and Marty Nussveltman were exploring the mathematical underpinnings of quantum field theory. Their calculations revealed disturbing inconsistencies, mathematical ghosts that suggested the standard model of particle physics, even with the Higgs boson, was profoundly incomplete. The equations predicted that quantum fluctuations should tear apart the fabric of space-time itself, making atoms impossible and rendering the universe a seething chaos of pure energy. Steven Weinberg, Sheldon Glashow, and Abdus Salam had achieved the seemingly impossible, unifying three of the four fundamental forces into a single theoretical framework. But gravity remained stubbornly separate, and more troubling still, their calculations revealed that without some unknown stabilizing mechanism, the energy of empty space should be so enormous that it would prevent the formation of any structured matter whatsoever. In the cathedral-like halls of CERN, where particle beams trace perfect circles through superconducting magnets, physicists began detecting whispers of the impossible. Subtle deviations in particle decay patterns emerged from the data, anomalies so small they could barely be distinguished from experimental noise, yet persistent enough to suggest something profound was operating beyond the reach of the standard model. The Large Hadron Collider, that 27-kilometer temple to human curiosity buried beneath the French-Swiss border, began revealing glimpses of physics that shouldn't exist according to established theory. Energy disappeared into dimensions that had no business being there. Particles behaved in ways that suggested they were interacting with invisible fields, communicating with aspects of reality that remain completely hidden from direct observation. At Fermilab, In the flat prairie lands of Illinois, the Tevatron accelerator detected hints of new particles, ephemeral signatures that appeared for microseconds before vanishing back into the quantum foam. These weren't the exotic particles that theorists had predicted. There was something entirely unexpected, something that seemed to be mediating between the world we can see and touch and the vast hidden sectors of reality that comprise 95% of the universe. The search intensified when dark matter and dark energy emerged from astronomical observations as the dominant components of cosmic reality. Suddenly, everything humanity had cataloged, every star, planet, and galaxy, appeared to be merely the visible foam on an ocean of invisible existence. But this invisible sector wasn't simply separate from ordinary matter. It was intimately connected to it through mechanisms that defied explanation. Deep underground at the KK laboratory in Japan, scientists working with neutrino detectors began registering events that challenged every assumption about these ghostly particles. Neutrinos, which should barely interact with matter at all, were showing signs of transformations that suggested they were accessing hidden dimensions or interacting with unknown fields that permeate empty space. The data streams flowing from observatories and accelerators worldwide began to tell a consistent story, one that filled physicists with equal measures of excitement and existential dread. The universe was far more complex and precarious than anyone had imagined. Beneath the stable surface of physical law lay a roiling quantum substrate that should have made reality impossible, yet somehow remained balanced on the knife's edge between existence and annihilation. The quest for the final particle had begun in earnest, driven by the growing realization that humanity's very existence depended on finding and understanding the cosmic force that prevents the universe from consuming itself in a cascade of quantum destruction. When nothing became everything, the revelation that would transform physics emerged not from exotic experiments or distant observations, but from the most fundamental calculations about the nature of empty space itself. What scientists discovered in the equations of quantum field theory was so profoundly disturbing that many initially refused to believe the mathematics. Empty space, they learned, is not empty at all. Every cubic centimeter of what appears to be perfect vacuum seethes with an invisible storm of virtual particles, electron-positron pairs, photons, and more exotic entities that flash into existence for impossibly brief moments before annihilating back into nothingness. These quantum fluctuations are not merely theoretical constructs. They produce measurable effects that have been verified in laboratories worldwide. But when physicists calculated the total energy of these fluctuations, they encountered a result so catastrophically large that it challenged the very possibility of existence. The energy density of empty space should be 10^120 times greater than observed, a number so vast that it would curve space-time into an infinitely small point, making atoms, molecules, and life itself impossible. Yet here stands the universe, serene and structured, with galaxies spinning in cosmic harmony and atoms maintaining their electronic shells with clockwork precision. Something is suppressing these quantum fluctuations, maintaining what physicists call the vacuum state, the lowest possible energy configuration of all quantum fields. But this vacuum state appears to be balanced precariously, like a ball resting on the peak of a hill rather than settled safely in a valley. The implications terrified even the most seasoned theoretical physicists. If the vacuum state is truly unstable, then at any moment, a random quantum fluctuation could trigger a cascade that would rewrite the laws of physics throughout the observable universe. This process, which scientists term vacuum decay, would propagate at the speed of light as an expanding sphere of destruction, annihilating everything in its path and replacing familiar physics with new laws under which atoms cannot exist. Einstein's equations of general relativity revealed another layer of the mystery. The cosmological constant, the parameter that describes the energy of empty space, should be enormous if quantum field theory is correct. Instead, observations show it to be incredibly small, just large enough to drive the universe's accelerating expansion through dark energy. This precise balance cannot be coincidental. Something must be actively maintaining this delicate equilibrium. At CERN, the world's most powerful particle accelerator began detecting hints that this balance might be more precarious than anyone had imagined. The mass of the Higgs boson, combined with the mass of the top quark, places the universe precisely at the boundary between stability and catastrophic collapse. These measurements suggest that the Higgs field itself, the very mechanism that gives mass to matter, might be slowly evolving toward a lower energy state that would trigger universal annihilation. The magnetic moment of the muon, measured with extraordinary precision at Fermilab, deviates from theoretical predictions by amounts that point to new particles or forces operating at the boundary between quantum mechanics and spacetime itself. These deviations suggest that the Standard Model is not merely incomplete, but fundamentally inadequate to describe the forces that maintain cosmic stability. More disturbing still, experiments at the Large Hadron Collider began revealing subtle signs that the laws of physics might not be as fixed as scientists had assumed. Particle interactions showed minute variations that suggested something was actively influencing the strength of fundamental forces, as if an invisible hand were constantly adjusting the cosmic controls to prevent reality from sliding into chaos. The scientific community faced an uncomfortable truth that challenged every assumption about the nature of existence. Either the universe was balanced on an impossibly precise knife's edge by pure chance, a scenario so unlikely that it defied rational acceptance, or something fundamental was maintaining this balance. The final particle, if it existed, would be reality's guardian, the cosmic mechanism that prevents the universe from destroying itself through its own quantum fluctuations. The search had become more than scientific curiosity. It had become an investigation into whether existence itself required active maintenance, whether consciousness and complexity could persist in a cosmos governed by blind chance, or whether some deeper principle was ensuring that the universe remained capable of producing stars, planets, and the intricate chemistry of life itself. Signals from the quantum realm, the hunt for the final particle, demanded technology that pushed human ingenuity to its absolute limits. Machines capable of probing the deepest layers of reality, where matter dissolves into pure mathematics and the familiar laws of physics give way to quantum strangeness. In laboratories buried miles beneath the Earth's surface, scientists constructed instruments sensitive enough to detect the whisper of a single particle interaction amid the cosmic storm of background radiation. The Large Hadron Collider underwent unprecedented upgrades. Its superconducting magnets cooled to temperatures colder than deep space. Its particle beams accelerated to energies that recreated conditions from the universe's first trillionths of a second. When protons collide at 99.999999 the speed of light, they shatter into cascades of exotic particles that exist for briefer moments than the time it takes light to cross an atomic nucleus. Yet within these ephemeral fragments, physicists began detecting patterns that suggested the presence of something far more fundamental. Deep underground at the Laser Interferometer Gravitational Wave Observatory, laser beams stretch across 4-kilometer arms with precision so exquisite that they can detect changes smaller than 1/10,000th the width of a proton. These instruments listen to the universe's gravitational songs, ripples in spacetime itself that carry information about cosmic events billions of years in the past. But buried within these gravitational waves, scientists found subtle harmonics that hinted at additional dimensions, extra forces, and particles that interact so weakly with ordinary matter that they pass through entire planets without leaving a trace. The Planck satellite mapped the cosmic microwave background radiation with unprecedented precision, capturing the afterglow of the Big Bang in exquisite detail. This ancient light carries encoded within its tiny temperature fluctuations the fingerprints of the universe's first moments, when the fundamental forces were unified and reality existed in a state of perfect symmetry. Hidden within these primordial patterns, cosmologists discovered anomalies that suggested the action of a stabilizing force, something that prevented the young universe from collapsing into chaos as it cooled and the fundamental forces separated. Miles beneath the surface, in abandoned mines and purpose-built caverns, neutrino detectors waited in absolute darkness for the arrival of these ghostly messengers from the cosmos. Neutrinos, produced in the nuclear furnaces of stars and the violent death throes of supernovae, barely interact with matter at all. Trillions pass through human bodies every second without leaving any trace. Yet these detectors began registering events that couldn't be explained by known neutrino physics. Interactions that suggested these particles were carrying information about quantum fields that exist beyond the standard model. The data was subtle, requiring years of patient observation to distinguish genuine signals from background noise. But gradually, a picture emerged of neutrinos that seemed to be oscillating not just between their three known types, but into additional states that suggested the existence of sterile neutrinos, particles that interact only through gravity and whatever force maintains cosmic stability. Most intriguingly, experiments designed to detect dark matter began registering correlated signals across multiple detectors worldwide. These weren't the massive, weakly interacting particles that theorists had predicted. Instead, they pointed to something that seemed to mediate between the visible and invisible sectors of reality, a bridge particle that maintained the delicate relationship between ordinary matter and the dark components that comprise most of the universe. Computer simulations running on the world's most powerful supercomputers revealed the full scope of the mystery. Models of the early universe showed that without some form of active stabilization, the cosmos should have either collapsed immediately under its own quantum fluctuations or expanded so rapidly that no structures could ever form. The fact that galaxies, stars, and planets exist at all proves that something has been actively maintaining the delicate balance of forces that makes complexity possible. The simulations also revealed something more disturbing. The stabilizing mechanism, whatever it was, appeared to be evolving over cosmic time. The same force that had maintained reality's coherence for 13.8 billion years was showing signs of gradual change, as if the universe's cosmic maintenance system was itself aging and potentially approaching some kind of fundamental transition. Advanced quantum field calculations performed on exascale computers mapped the complete mathematical landscape of possible vacuum states, revealing a topology so complex that it resembled a vast mountain range of energy peaks and valleys. The universe appeared to be perched on one of these peaks, maintained in an unstable equilibrium by forces that operated at the intersection of quantum mechanics and general relativity. The convergent evidence from multiple independent experiments pointed to an inescapable conclusion: reality required active maintenance. The final particle, whatever its nature, was the cosmic mechanism that prevented the universe from sliding into a lower energy state that would annihilate everything we know and love. Finding it had become not just a scientific quest, but a race against time itself. The accelerating mystery as the search for the final particle intensified, scientists made a discovery that transformed their understanding of the cosmic stakes involved. The universe's expansion, which had been slowing down due to the gravitational pull of matter, was actually accelerating. Something was driving the cosmos apart with ever-increasing force, stretching the fabric of space-time itself in ways that defied every prediction of conventional physics. This acceleration was attributed to dark energy, a mysterious force that comprises nearly 70% of the universe, yet remains completely invisible to direct observation. But as astronomers studied this phenomenon more carefully, they realized that dark energy was not constant. It was growing stronger over cosmic time. The vacuum state of the universe was not static, but evolving, potentially becoming less stable as eons passed. The implications were staggering. If the vacuum state was indeed evolving, then the same quantum fluctuations that should have destroyed the universe 13.8 billion years ago might still pose an existential threat. The final particle, rather than providing permanent stability, might be fighting a losing battle against the inexorable pull of entropy and quantum uncertainty. Theoretical calculations revealed a scenario that filled cosmologists with existential dread. The universe might exist in what physicists call a false vacuum, a state that appears stable on human timescales but is actually metastable over cosmic time, like a supercooled liquid that can crystallize instantly when disturbed. The cosmic vacuum could undergo a spontaneous phase transition that would propagate throughout the observable universe at the speed of light. Advanced particle physics experiments began detecting quantum field fluctuations that grew stronger with each passing year. The fabric of space-time itself showed signs of stress, like a material approaching its breaking point under invisible forces. Gravitational wave detectors registered subtle changes in the patterns of cosmic ripples, suggesting that the fundamental constants of physics, the speed of light, the strength of gravity, the mass of elementary particles, might not be as constant as scientists had assumed. The Higgs field, rather than maintaining a stable vacuum state, appeared to be slowly evolving toward a lower energy configuration. Precise measurements of the Higgs boson mass and its interactions with other particles place the universe in a region of parameter space that cosmologists termed metastable, stable for now, but potentially vulnerable to catastrophic transitions that could occur without warning. If this process continued, it could trigger the formation of a bubble of true vacuum, a region where the laws of physics would be completely different from those in our current universe. This bubble would expand at the speed of light, its boundary marking the advancing edge of annihilation. Everything within would be governed by new physical laws under which atoms, chemistry, and life could not exist. More disturbing still, some experiments suggested this process might already have begun. Anomalous particle decays detected at the Large Hadron Collider showed patterns that could be interpreted as early signs of vacuum instability. Energy seemed to be disappearing into unknown channels, as if particles were beginning to interact with aspects of reality that remain hidden from direct observation. The magnetic anomaly of the muon, the discrepancy between theoretical predictions and experimental measurements, grew more pronounced with each new round of experiments. This deviation suggested that new particles or forces were becoming more active over time, potentially signaling the early stages of a cosmic phase transition that could reshape reality itself. Neutrino experiments detected oscillation patterns that couldn't be explained by known physics, suggesting that these ghostly particles were accessing hidden dimensions or interacting with fields that exist at the boundary between stability and chaos. The data hinted at a universe far more complex and dynamic than the static picture painted by the Standard Model. The final particle, if it existed, was revealed to be not just a stabilizing force, but potentially the mechanism by which cosmic evolution proceeded. It might be the universe's way of exploring different physical configurations, testing new ways of organizing matter and energy in an endless quest for optimal stability. But optimization in physics often requires passing through unstable intermediate states. The final particle might be guiding the universe through a cosmic metamorphosis, a transformation that could take billions of years to complete, but would ultimately result in a fundamentally different kind of reality. Whether this transformation would preserve the possibility of life and consciousness remained an open question that haunted physicists worldwide. The race to find the final particle had become a race to understand whether humanity existed during a period of cosmic stability or in the midst of the universe's most dramatic transition, a metamorphosis that would determine the fate of everything that had ever existed or ever could exist. The mathematics of eternity, the theoretical landscape surrounding the final particle, stretched across the most abstract realms of mathematical physics, where equations became windows into dimensions beyond human perception and symmetries revealed the hidden architecture of reality itself. Leading theories propose that this ultimate constituent of existence dwelled at the intersection of quantum mechanics and general relativity, the long-sought quantum gravity particle that would finally unite Einstein's spacetime with Heisenberg's uncertainty principle. String theory, perhaps the most ambitious attempt to describe reality's fundamental nature, suggested that the final particle might be the graviton, the hypothetical quantum of gravitational force. But unlike the familiar particles that inhabit our three-dimensional world, this graviton would exist in the higher dimensions that string theory requires for mathematical consistency. These extra dimensions, compactified into spaces smaller than atomic nuclei, could harbor entire universes of particles and forces that influence our reality while remaining completely hidden from direct observation. In the elegant mathematics of string theory, particles are not point-like objects but tiny vibrating loops of energy, each vibration mode corresponding to a different type of particle. The final particle might be a particular harmonic of these cosmic strings, a vibration pattern that maintains the tension necessary to keep the higher dimensions stable and prevent them from either expanding catastrophically or collapsing into nothingness. Loop quantum gravity offered a radically different vision, proposing that space-time itself is quantized, woven from discrete units at the Planck scale, where distances become so small that the very notion of continuous space breaks down. In this view, the final particle might be these quantum units of space-time themselves, constantly creating and destroying the fabric of reality in a cosmic dance that maintains the universe's structural integrity while allowing for the flexibility necessary for quantum phenomena. The mathematics revealed something profound. At the Planck scale, the distinction between matter and space-time dissolves. The final particle might not be a thing that moves through space and time, but rather the fundamental process by which space and time are continuously recreated. Reality becomes a verb rather than a noun, a dynamic process of cosmic maintenance that manifests as the stable universe we observe. The holographic principle, emerging from black hole physics, suggested an even more radical possibility. All the information contained in our three-dimensional universe might be encoded on a two-dimensional surface at the cosmic boundary, like a hologram that projects the illusion of depth. The final particle might be the mechanism by which this cosmic information is processed and maintained, ensuring that the holographic projection we call reality remains stable and coherent across vast scales of space and time. This perspective suggested that consciousness itself might play a fundamental role in cosmic stability. If reality is information being processed, then observers, beings capable of measuring and recording quantum states, might be necessary components of the universe's self-maintenance system. The final particle could be the interface between mind and matter, the quantum mechanical mechanism by which observation collapses wave functions and maintains the coherent classical reality that emerges from quantum chaos. Supersymmetry theories propose that every known particle has a massive superpartner existing in parallel dimensions. The final particle might be the lightest supersymmetric particle, the gravitino, or a superpartner of the Higgs boson, serving as the bridge between our visible universe and the invisible supersymmetric sector that provides the universe's hidden stability. This particle would be stable by virtue of a fundamental symmetry that prevents it from decaying, making it an ideal candidate for both dark matter and cosmic stabilization. Extra-dimensional theories suggested that our four-dimensional space-time is embedded like a membrane in a higher-dimensional bulk space. The final particle might be a bulk particle capable of moving freely through all dimensions, serving as the cosmic traffic controller that prevents dimensional boundaries from collapsing and maintains the precise geometry necessary for stable matter and forces. The most radical theoretical framework proposed that the final particle is not a physical entity at all, but pure information, a mathematical structure that ensures the universe's laws remain consistent and prevents logical paradoxes from destroying reality. In this view, the laws of physics are not discovered but computed, and consciousness represents the universe's method of performing the calculations necessary to maintain its own existence. Each theoretical framework made specific predictions about experimental signatures, but the final particle remained tantalizingly beyond the reach of current detection capabilities. The mathematics suggested that finding it would require not just more powerful instruments, but fundamentally new ways of thinking about the relationship between matter, information, and consciousness, a conceptual revolution that would transform humanity's understanding of its place in the cosmic order. Machines that touch infinity, the technology required to detect the final particle, push the boundaries of human engineering into realms where the distinction between science and art begins to blur. In laboratories that resemble cathedrals of precision, scientists constructed instruments capable of measuring phenomena so subtle that they exist at the very limits of physical possibility, where quantum mechanics and classical physics merge into a unified description of reality's deepest foundations. The future circular collider, planned for completion in the 2040s, will stretch 100 kilometers in circumference beneath the European countryside, its superconducting magnets generating fields strong enough to bend the paths of particles traveling at nearly the speed of light. This machine will accelerate particles to energies that approach the Planck scale, the fundamental quantum of energy where space-time itself begins to fluctuate and the familiar laws of physics give way to the more fundamental principles that govern reality's architecture. At these energies, particle collisions will recreate conditions that existed during the universe's first 10 to 43 seconds, when gravity and quantum mechanics were unified in a single force and the fundamental constants of nature were still crystallizing into their current values. If the final particle exists at the intersection of these forces, the future circular collider will either discover it directly or reveal its influence on other particles in ways that current theory cannot predict. The Laser Interferometer Space Antenna will deploy 3 spacecraft in a triangular formation millions of kilometers apart, creating the largest scientific instrument ever built. Free from Earth's seismic vibrations and atmospheric disturbances, this space-based gravitational wave detector will observe ripples in space-time with unprecedented sensitivity, capable of detecting distortions smaller than the quantum fluctuations that limit terrestrial experiments. These observations will reveal whether space-time itself is stable or undergoing subtle evolution that signals the final particle's activity across cosmic distances. If reality requires active maintenance, the gravitational wave signatures of this cosmic engineering project will be written into the very fabric of space and time, waiting for instruments sensitive enough to read the universe's maintenance logs. Quantum computers represent perhaps the most revolutionary tool in the search for ultimate understanding. Unlike classical computers that process information sequentially, quantum computers exploit the strange properties of quantum superposition and entanglement to perform calculations that would be impossible for any conceivable classical machine. These devices are being specifically designed to simulate the behavior of quantum fields at scales and complexities that mirror the universe itself. By creating digital universes governed by the same quantum mechanical laws that operate in reality, scientists can test whether proposed final particles can actually stabilize the vacuum state under realistic cosmic conditions. These simulations will reveal whether the mathematical theories that seem elegant on paper can actually produce the stable, structured universe we observe around us. The James Webb Space Telescope and its planned successors will map the universe's large-scale structure with extraordinary precision, searching for patterns that reveal the influence of stabilizing forces across cosmic history. Any deviation from the predicted evolution of galactic clusters, dark matter distributions, or the cosmic web itself could signal the final particle's activity on the largest possible scales. These observations will trace the universe's history from its earliest moments to the present day, looking for signs that cosmic evolution has been guided by hidden principles rather than proceeding according to pure chance. If the final particle maintains cosmic stability, its influence should be detectable in the way matter organized itself into the complex structures that eventually gave rise to stars, planets, and life. Underground laboratories are being redesigned with technologies that seem almost magical in their sensitivity. Dark matter detectors cooled to temperatures approaching absolute zero can register the recoil energy from a single particle interaction, while neutrino experiments buried miles beneath the Earth's surface count individual particles that have traveled millions of light years from distant supernovae. These facilities are expanding their search beyond dark matter to look for any exotic particles that mediate between different sectors of reality. The most advanced experiments can distinguish between different types of particle interactions with precision that approaches the fundamental quantum limits, making them capable of detecting even the most weakly interacting final particles. Perhaps the most ambitious undertaking involves mapping the complete mathematical landscape of quantum field theory using exascale supercomputers that perform quintillions of calculations per second. These machines are calculating the positions and properties of all possible vacuum states, creating detailed maps of the energy landscape that determines whether the universe is stable, metastable, or doomed to eventual collapse. The computational requirements are staggering. Simulating even a small region of space-time at the quantum level requires more processing power than all previous human computational efforts combined. Yet these calculations are revealing the mathematical foundations of existence itself, showing how the universe maintains its coherent structure despite the quantum chaos that lurks beneath the surface of apparent stability. The weight of ultimate questions, the search for the final particle, has become more than a scientific quest. It has evolved into humanity's deepest philosophical investigation into the nature of existence itself. As instruments probe deeper into the quantum foundations of reality and theories stretch toward the ultimate limits of mathematical possibility, scientists find themselves confronting questions that transcend the traditional boundaries between physics and metaphysics, between science and spirituality. If the final particle exists, it suggests that the universe is not a random accident, but a carefully orchestrated system requiring constant maintenance and adjustment. This revelation would fundamentally alter humanity's understanding of its place in the cosmic order, suggesting that consciousness and intelligence might not be mere byproducts of chemical evolution, but integral components of the universe's self-maintenance mechanism. The implications ripple through every aspect of human understanding. The precision required to maintain cosmic stability, to balance quantum fluctuations, regulate the fundamental constants, and prevent vacuum decay, suggests a level of cosmic engineering that challenges materialist assumptions about the nature of reality. Whether this engineering emerges from natural processes, represents the activity of some form of cosmic intelligence, or indicates that consciousness itself plays a fundamental role in maintaining reality, remains an open question that haunts physicists and philosophers alike. Yet if the final particle is never found, the implications are equally profound. A universe without active stabilization would be fundamentally unstable, a temporary pattern in an infinite landscape of possible realities. Humanity and all the complexity that surrounds us would represent a fleeting accident, destined to eventually disappear without leaving any trace that we ever existed. This possibility confronts us with questions about meaning, purpose, and the significance of our brief moment of awareness in an indifferent cosmos. The philosophical weight of these possibilities has begun to influence the search itself. Scientists recognize that they are not merely investigating another aspect of physical reality, but potentially uncovering the deepest truths about existence, consciousness, and the relationship between mind and matter. Some theories suggest that observation and measurement play fundamental roles in quantum mechanics, not as mere technical details, but as necessary components of reality's self-maintenance system. This perspective suggests that consciousness might be intimately connected to the final particle's function. Quantum mechanics requires observers to collapse wave functions and select specific outcomes from quantum superpositions. If the universe requires active maintenance, conscious observation might be one of the mechanisms by which this maintenance is performed. In searching for the final particle, humanity might be participating in the very process that keeps reality stable and coherent. The search has also revealed the magnificent audacity of conscious beings arising from unconscious matter. We are patterns of organized atoms that have become aware of themselves and capable of questioning the deepest foundations of existence. Whether the universe inevitably produces such self-aware patterns, or whether consciousness represents an unlikely accident, remains one of the most profound mysteries in science. The final particle, if it exists, might be the universe's method of ensuring that complexity can emerge and persist long enough for conscious observers to evolve. In this view, the cosmos is not merely a collection of particles and forces, but a vast system optimized for the emergence of intelligence, beauty, and understanding. The laws of physics might be fine-tuned, not by external design, but by internal evolutionary processes that favor universes capable of producing observers. Contemporary physics has revealed that reality is far stranger and more wonderful than our ancestors imagined. Quantum mechanics shows that particles exist in multiple states simultaneously until observed. Relativity demonstrates that space and time are flexible and dynamic rather than fixed. String theory suggests that our familiar three-dimensional world might be a projection from higher dimensions, while the holographic principle implies that all physical reality might be information processing at cosmic scales. The search for the final particle sits at the confluence of all these revolutionary insights, promising to either confirm our deepest theories or overturn them entirely. Whether reality is maintained by an undiscovered particle, sustained by mathematical principles that exist beyond physical matter, or preserved by the interplay of consciousness and quantum mechanics, the quest has already transformed our understanding of what it means to exist in a universe that somehow permits the existence of beings capable of asking why it exists at all. In the end, the final particle remains hidden, perhaps forever beyond direct detection. But the search itself has revealed that the greatest mystery might not be what holds the universe together, but why it chose to create observers capable of wondering about its deepest secrets. In seeking the final piece of the cosmic puzzle, we discover that we ourselves might be an essential part of the answer. Conscious patterns in the quantum field, temporary arrangements of matter and energy that have become capable of contemplating the infinite mystery of their own existence. Whether we find the final particle or it remains forever elusive, the quest has already shown us that we live in a universe far more strange and beautiful than we ever dared imagine. A cosmos where consciousness and quantum mechanics dance together in patterns that may hold the key to understanding not just what the universe is, but why it is at all.